Mass spectrometry is the ultimate scale for chemists. It identifies molecules by measuring their exact mass-to-charge ratio as they fly through a vacuum. But for decades, the standard way to do this was a brute force method called electron impact ionization. You first vaporize a sample and then blast it with a beam of electrons carrying about 70 electron volts of energy. This diagram illustrates the flaw. Hitting a complex molecule with high energy shatters it. The neopentane molecule breaks into fragment peaks at 57, 41, and 29. The data lacks the parent molecular ion peak, the crucial point needed to identify the intact molecule. This physical limitation kept scientists from analyzing the massive, fragile molecules that actually drive biology, like large proteins or polar salts. They would simply disintegrate before they could be weighed. Analyzing these biological giants required researchers to solve a specific physics problem: how to impart enough energy to charge a molecule without shattering its chemical bonds. The solution was to stop vaporizing the sample directly. Instead, chemists learned to surround the delicate target molecule inside a chemical shield called a matrix. One of the first major techniques to use this principle was Fast Atom Bombardment, which relies on a thick, viscous liquid matrix, like glycerol, to house the sample. Instead of shooting electrons, this method fires a high-voltage beam of heavy neutral atoms, usually xenon or argon, straight at the liquid. This schematic shows the xenon beam striking the matrix mixture, causing a plasma plume to erupt toward the lenses. The liquid matrix absorbs the kinetic impact, converting it to heat, which gently lifts the intact molecule into the gas phase. However, that violent collision also shatters the liquid matrix itself. All those broken glycerol pieces fly into the mass spectrometer alongside your target, creating a noisy, chaotic background in the lower mass range of the data. The liquid matrix proved that a protective buffer could keep large molecules intact. But to weigh even larger, more complex targets clearly, researchers needed a way to deliver energy with absolute precision. That need led to MALDI, Matrix-Assisted Laser Desorption Ionization, a technique designed to handle massive biomolecules. MALDI abandons the liquid bath. Instead, the sample is highly diluted into a solution with a solid organic matrix, like nicotinic acid, and then dried down into a crystal lattice on a metal plate. This diagram shows the MALDI process. A nitrogen laser hits the solid crystalline mixture with intense light pulses. The matrix acts as a sponge, strongly absorbing that exact wavelength. It evaporates instantly, creating a gas plume where the target molecule gains a positive charge. The target molecule is then pulled into the mass analyzer, free of its solid casing, carrying an electrical charge and experiencing almost zero fragmentation. By tuning the laser directly to the matrix and not the sample, the matrix takes the entire energetic hit. The biomolecule is carried along for the ride, completely safe. When you combine these soft ionization techniques with analyzers that can measure extremely long flight times, the scale of analysis expands enormously. Mass spectrometers went from being tools that could only weigh small volatile gases to instruments capable of weighing massive biopolymers. This chart shows the MALDI spectrum of a monoclonal antibody. On the far right is a towering peak labeled M+, at roughly 149,190 mass-to-charge ratio. This single, clean peak proves a protein weighing almost 150,000 daltons survived the transition into the gas phase entirely intact. By engineering a way to route destructive energy through chemical matrices, FAB and MALDI neutralized the threat of fragmentation. This shift moved mass spectrometry beyond the analysis of small gases, establishing it as a primary tool for mapping the complex proteins of human life.